In this video, we'll look at different periodic trends. The first trend we're going to look at is size of atoms. We kind of have an idea already that the atomic size is going to increase as the principal quantum number n increases. So as n increases, the probability of the outer electrons will be further from the nucleus increases. So that's saying when we go down the periodic table, we're increasing n. So remember, we go from our 1s2 to our 2s2 to our 3s2. We're increasing in size every time we increase that principal quantum number. And then the size of our atoms are going to decrease as the effective nuclear charge increases. So the effective nuclear charge is how much pull the electrons feel towards the nucleus. And the greater the pull, the closer the electrons will be towards that nucleus. So therefore, that's going to decrease the size of our atom. So as the effective nuclear charge increases, the outer shell electrons are going to be pulled closer to the nucleus. And then for main group elements, the atom size increases as you go down a group on the periodic table and decreases as you go across the table. Note that's only for the main group elements. Looking at our main group elements, we can see the bonding atomic radius tends to decrease as you go from left to right. So we start with our larger atoms here, lithium, and then it gets smaller and smaller as you go across the periodic table towards fluorine, which as we can see is much smaller than our lithium atom. It also tends to increase as we go down a column. So if we start at the top here, hydrogen, lithium, sodium, potassium, rubidium, cesium, you can see we increase in size as we go down the periodic table. No matter which row we do, we can see when we start from our alkali metals and we go across to our halogens, they always get smaller. And that's because the halogens have a greater effective nuclear charge. One thing to note is when we're looking at our transition metals, you can see that the atomic radius doesn't really change much. They stay about the same size as we go across with our transition metals. It's really only for the main group ones that we can see the size decrease as we go across the periodic table. Now that we've seen a little bit about neutral main group atoms, time to look at ions. When we're looking at our ions, the ions are going to increase in size as you go down a column. So again, on the top, we're going to have our smaller atoms. And then as we go down a column, we end up with our larger atoms. And then the ion size is going to depend on the nuclear charge, the number of electrons it has, and the orbital that the electrons reside in. So something in the n equals 2 orbital is going to be much smaller than something in the n equals 3 orbital, even if it's an ion. Breaking down these ions, first we look at cations. Cations are smaller than their parent atom. So the cations actually end up smaller than the neutral atom. So a lithium ion is much smaller than a lithium. A sodium ion is much smaller than a sodium. And this is because we've lost that outer shell electron. If we lose the outer shell electron, we've gone down in the principal quantum number. And so that's one reason why the ions are smaller. And the greater the charge on the ion, so you can see magnesium is a +2, that's much smaller than our sodium, which is just a +1. And we can see that happens between potassium and calcium as well. Or even between sodium, magnesium, and aluminum. Aluminum is a +3. You can see how much smaller it gets compared to sodium. So whenever we have our metals, and they're losing electrons, so we're getting a larger and larger amount of cation there, a larger positive charge, we end up with smaller and smaller ions. The exact opposite is true with anions. Anions are always larger than their parent ion. So anions, when they become charged, get bigger. And the more negative charge, the bigger it gets. So we can see we have a chlorine here, and then we have a chloride with a minus charge. We have a sulfur, and then we have a sulfide with a minus charge. We can see that they end up bigger with the more negative charge it has. And this is because we're adding electrons into our system, and the electrons want to repel each other. Since the electrons want to repel each other, the size of the orbital actually increases and pushes further away from the nucleus. So now if we want to practice this idea, and I want to arrange sodium, beryllium, and magnesium in order of increasing atomic radii. First thing I want to note, they're all neutral. So since they're all neutral, I want to follow the trend on my periodic table where I go from my larger atoms in the bottom corner to my smaller atoms in the top corner here. And I go from larger up to smaller. And so if I look at my periodic table, I can start to arrange these in order. And when I arrange them, beryllium is my smallest element. Magnesium is next because magnesium is right underneath beryllium. And then sodium is next because sodium is next to magnesium. Not too bad, right? We just have to look at our periodic table. Now let's talk about ions. Let's practice with our cations. When we're looking at magnesium ion, calcium ion, and a plain calcium, I want to arrange these in order of decreasing atomic radius. First thing I know, since I have a positive charge, I have a cation, my ion is going to be smaller than the parent neutral atom. So remember, cations are smaller. And the more cation, the more positive charge I have, the smaller it is. But we can see we have a +2 charge and a +2 charge. So then we have to look at their location on the periodic table. And calcium is right underneath magnesium. Calcium is one principal quantum number larger than magnesium. So therefore, calcium plus is still going to be larger than magnesium plus. So when I arrange it from the largest one, the neutral calcium, to the second largest, the calcium ion, to the smallest one, the magnesium ion. So looking at all these different ions, we can create what we call an isoelectric series. An isoelectric series has ions that have the same number of electrons. It doesn't matter what that ion is as long as it has the same number of electrons. And then so as their nuclear charge increases in an isoelectric series, the ions become smaller. So if we look at that, I have oxygen or an oxide ion with a -2 charge, fluoride ion with a -1 charge, neon, sodium plus, and magnesium ion. All of these different elements in their ion form have the same 10 electrons. They all have 10 electrons, and they all have the electronic configuration of 1s2, 2s2, 2p6. And so when I arrange it, the anions are always going to be larger than the cations. So I'd arrange my anions in the largest form. The neutral atom is next, and then the cations are smaller. When we have an isoelectric series, that's when our atoms have the same number of electrons. We can see when we're looking at our isoelectric series, ionic size decreases as our nuclear charge increases. Now that we've looked a little bit at size, let's start looking at ionization energy, our next periodic trend. Now that we've looked a little bit at size, let's start looking at our next periodic trend, ionization energy. The ionization energy is the energy required to completely remove 1 mole of electrons from 1 mole of atoms. So it's essentially how much energy does it take to remove an electron from our atom. Atoms with low ionization energies tend to form cations because it's easy to remove that electron. It doesn't take much energy to get that electron out of the atom. Atoms with high ionization energies tend to form anions, except for noble gases. And that's because it takes a lot of energy to remove an electron. They don't want to lose that electron. So ionization energy tends to decrease as we go down a group and increase as we go across a period. Kind of makes sense. They tend to decrease as we go down a group because we're getting larger and larger atoms. So the electron is further and further away from the nucleus. It doesn't feel the pull of the nucleus as much. When we're looking at our ionization energy, there's different ones. So we have our first ionization energy, and that's the energy that is required to remove the first electron from an atom. So that would be the energy required to go from a calcium to a calcium plus 1. That would be our first ionization energy. Our second ionization energy is the energy it takes to remove the second electron. So that means we're going from a calcium plus 1 to a calcium plus 2. And we've lost another electron. Note when we're doing the second ionization energy, we already start with a cation. I'm already starting with calcium plus 1. And then I'm just creating calcium plus 2. And we can keep going on our ionization energies. I can have a third ionization energy, fourth, fifth, sixth, as many electrons as the atom has. It has ionization energies associated with that. And we can see a trend with this first ionization energy. With the first ionization energy, that's removing that first electron. Whenever we hit the noble gas, we can see that takes a lot of energy to remove that one electron. And then it becomes much easier once we start with the alkali metal to remove the first electron. It starts to slowly become harder, till we hit the next noble gas, and it becomes very hard. So you can see here's fluorine. It's extremely hard to remove an electron from a fluorine. Fluorine really wants to get that electron, not lose it. Neon doesn't want to lose electrons, but then go all the way down here to sodium. It really wants to give up that electron. And you can see that trend continue as we go down the periodic table. When we're going across a row, it starts to become harder and harder to lose an electron till we hit the noble gas, and that's the hardest one in each row. Then the ionization energy drops really far down when we hit the next row and we start with the alkali metal. And then it goes up again and then down. You can also notice if we're looking at the noble gases here, it becomes slightly easier and the ionization energy becomes slightly less as we're going down the column. We can even see the same thing happening with the alkali metals. It becomes ever so slightly easier as we're going down the column for the alkali metals. So looking at this trend of ionization energies and then asking a question. We know that the larger the ionization energy, the more difficult it is to remove an electron. So which has a larger first ionization energy, arsenic or krypton? Well, if we look at our periodic table down here and we look at our trend, we have arsenic here. It has 947 kilojoules per mole to remove the electron. Krypton, the noble gas, has 1,351. So obviously, harder to remove an electron from krypton. That has a larger first ionization energy. We can even figure it out without looking at the numbers. We just look at our trend. And we can see our trend kind of goes up and across the periodic table. From the easiest to the hardest. Or from the lowest energy to the highest energy. We can see this trend follows the exact same as the size of our atoms. The larger the atom, the lower the ionization energy. The smaller the atom, the higher the ionization energy. Those two trends follow each other. Also makes sense, right? The larger the atom, the further away that electron is from the nucleus. So the easier it is to lose that electron when it's so far out. The smaller the atom, the harder it is to lose that electron because it's so close to the nucleus. So one question about this ionization energy. Why is it not always increasing as we go across the group? If I look at row 2, we start lithium, beryllium takes more. Boron's actually easier to ionize than beryllium. Up to nitrogen. And then oxygen actually is a little easier to ionize than nitrogen. What's going on here? What's up with the difference between beryllium and boron and nitrogen and oxygen? They don't seem to be following this trend. We can think of it as full shell or half shell stability. So if we think about our electron configurations, and I look at nitrogen, it has a configuration of 2p3. I have 3 electrons in that p orbital. It's exactly half full. Half full is sort of stable. Completely full is really stable. Half full is sort of. So nitrogen's already in a somewhat stable configuration. Each electron in the p orbital is in its separate orbital. Nothing is paired. Oxygen comes along and pairs up one of the electrons, and then there's 2 unpaired ones. If nitrogen has everything unpaired, changing that configuration will make it slightly less stable. Oxygen, on the other hand, has 1 that's paired up. If I get rid of that 1 electron, then I have a half-filled shell, slightly more stable. So that could be why oxygen is easier to ionize with the first ionization energy versus nitrogen. And we can say the same thing happens with boron and beryllium. Boron, if I get rid of 1 electron, it's emptied out its p orbitals. There's nothing in the p orbital. So that makes it a little more stable, having something completely empty, just like beryllium does. Beryllium has a 2s that's completely full and a 2p that's completely empty. I'd have to break that full 2s orbital to remove an electron from beryllium. So that's why beryllium is a little harder to ionize versus boron. Same thing with oxygen and nitrogen. Now let's look at successive ionizations. Let's look at that second ionization, that third ionization. So that's what our table is showing here. First ionization is this column. The second column is the second ionization, third ionization, fourth, fifth, sixth, seventh. So this would be removing 7 electrons from the atom. So if I look at sodium, sodium's first ionization is 496 kilojoules per mole. The second ionization, so that would be going from a sodium plus to a sodium plus 2, goes from 400 to 4,000, 10 times as much energy to remove that second electron. And you can see it's because when we break into the inner shell, we break into the core electrons here. So anything shaded here, these are core electrons. We can even see with magnesium, first ionization, 700, second ionization, 1400, third ionization, 7,000. That's a pretty big jump. So we're essentially looking at our metal as a +1 here, our metal as a +2 charge, our metal as a +3 charge, metal as a +4, +5, and so on. So we can even look at aluminum. We know aluminum typically forms a +3 charge, right? We can see why. It removes 3 valence electrons. It doesn't form a +4 charge. We can also see why. To get that +4 charge for aluminum, we'd have to use 11,000 kilojoules of energy just to remove that 4th electron versus 2,000, almost 3,000 versus 11.5. Big difference here. So when we're looking at our ionization energies, focusing on aluminum, if I start with aluminum, I get aluminum plus 1 doing our first ionization energy. It's 578. Aluminum plus 1 to aluminum plus 2 gives me a second ionization energy. Aluminum plus 2 to aluminum plus 3, the usual charge of aluminum, is my third ionization energy at 2,700 kilojoules per mole. Aluminum plus 3 to the next one, plus 4, that's too much energy. That's the core electron that we're taking out here. That's why it's so much larger than all the others. This is when we remove our core electron. So you can see we never really want to lose our core electron. We always want to keep the core electrons with the atom. And we can look at this in terms of electron configurations. Looking at aluminum, its electron configuration is neon, 3s2, 3p1. After its last 3 electrons, it forms that plus 3 charge, its typical charge. Now it has the same configuration as neon. It's isoelectric with neon. But once I try and make aluminum plus 4, I had to break into that neon and start breaking into core electrons. So I actually end up with helium, 2s2, 2p5. So that's why it takes so much more energy, is because I had to break into the next quantum number, the next principal quantum number, to get that charge. I had to use a core electron in order to get that charge. Summarizing our ionization energies, particularly focusing on the first ionization energy. So this is really focusing on our first ionization energy here. We start from our lowest and work our way up to the highest ionization energies. We can also note that the ionization energy trend follows the exact same one for atom size. So ionization energy and atom size follow the exact same trend. And now let's look at the opposite effect, electron affinity. If ionization energy is removing an electron, electron affinity is gaining that electron. So if I look at my electron affinity, that's going to be how much energy change it takes to add 1 mole of electrons to 1 mole of atoms. So atoms with low electron affinities tend to be cations. They don't want that electron. Atoms with high electron affinities tend to be anions. They really want that electron. And so one thing to note, the electron affinities are not as regular as those for atom size or ionization energies. In general, our electron affinity becomes more negative, more exothermic, as you go from left to right across the periodic table. So as we go from lithium across to fluorine, you can see our number becomes more negative. Fluorine really wants that electron. That's why it has such a negative electron affinity. Oxygen really wants an electron. Nitrogen, not so much. But we know why with nitrogen. We're changing that half-filled shell. Same thing happens with beryllium. We're changing the empty shell. And since we're starting to fill an empty shell here, and then we're breaking the half shell stability, that's why those two numbers end up being positive. It actually takes a little bit of energy to add that electron. These other ones, they really want that electron. Now let's compare ionization energy and that electron affinity. So both are measures of energy change, just the opposite process. Ionization energy is losing an electron. Electron affinity is gaining that electron. Ionization energy is always positive, so it always requires energy to remove an electron. Electron affinity can be positive or negative. Noble gases have a positive one because it requires energy to add electrons to noble gas. They don't like to change. Most have negative electron affinities, so they'll actually lose energy when an electron is added. They really want that electron. it becomes more stable for them to have that electron. So summarizing our three different trends. Atomic size, we go from our smaller to our larger, or you can think we go from larger to smaller. Ionization energy, we go from our lower ionization energies to our larger ionization energies. So these down here really want to give up their electrons. The ones up here really don't want to give up their electrons. And the opposite electron affinity, up here, they really want to gain that electron. Down here, they really don't. But electron affinity has a lot more exceptions than ionization energy. And now a quick look at metallic behavior. Metals are typically shiny solids with moderate to high melting points. They're also good conductors of heat and electricity, and they can be easily shaped. This is how we can get metal sheets, metal wires, anything. Metals tend to lose electrons to form cations, so they're easily oxidized, which means metals tend to be strong reducing agents. And most metals form ionic oxides, which are basic when we add them to aqueous solutions. So most metal oxides are basic. And we can think metallic behavior goes from very little metallic behavior in the top corner down to very metallic behavior in our bottom corner here near cesium and francium. So cesium has one of our most metallic behavior elements. Fluorine, one of our least. And so summarizing all of our different periodic trends, we can see atomic radius increases as we go across the column backwards and down. So our bottom corner here has our largest elements. They also have our lowest ionization energies and our highest electron affinities. They also have our lowest ionization energies. In our top corner here, we have our nonmetals. So they have a lot of nonmetal characteristic. They usually are smaller atoms. They usually have higher ionization energies. And they also have higher electron affinities. So they want to gain an electron. Now you guys should be familiar with all of our different periodic trends and should be able to predict a little bit about the atoms based on their location on the periodic table.